Welcome, Kirkwood School District Sound and Light, 6th grade science. Our goal today is we are going to look at describing how sound energy can be transferred by waves. So you can see there's a speaker there, and you can imagine if it were making a sound, how that sound is transferred by a wave. First of all, we need to define sound. Sound is a disturbance that travels through a medium as a longitudinal wave. So as the speaker moves back and forth, that is also causing the air particles to move throughout the medium back and forth. How does a sound wave begin? Well, all sound waves begin with a vibration. As soon as a medium is disturbed, that means energy has been placed into the system, causing a disturbance, that sound wave begins to move or propagate throughout the medium. When we think about this, we actually can visualize that. There's a really cool video here on YouTube. I'm going to kind of load it up real quick. And it's a really neat video to show simply just how you can make sound visual, a visual representation. So here what you have is you've got sort of a layer of fabric over the top of a set of speakers. And you can hear the sound. And as those sounds change frequency, pitch or loudness, they change the shape of the object or the arrangement of salt there, as you can see on the screen. Now, how does this have anything to do with waves? Well, the wave is causing a disturbance. The medium, in this case, is that fabric. And we can see that the changing of those different pitches or sounds cause the medium to vibrate and change different. It's pretty amazing, although it gets so loud that I can barely handle listening to it. So I'm going to move on past it. So how do sound waves travel through the air? Well, the vibrations disturb those nearby particles. Each time a gong or a cymbal or a speaker or a drum moves to the right or to the up or down or to the left, it pushes air particles together. This creates a compression. When that drum or when those vocal cords move to the left, the particles bounce back and spread out, creating a rarefaction. These compressions and rarefactions back and forth create this wave that travels through the air from the source to the receiver. You are, in this case, the receiver. So sound can travel through a lot of things. It can travel through air, which is what you're kind of used to, because right now my voice is traveling through air to the microphone. If that air was not there, my voice would not be able to get to the microphone. But sound can also travel through other things, solids and liquids too. So if you are, let's say, in one room and you can hear somebody talking kind of through the wall, well, you can imagine that that energy coming from the voice is being transferred to the wall, causing the wall to vibrate. That, of course, is sound waves moving through a medium. Can also travel through liquids, which, of course, if you've ever seen any documentaries about whales or dolphins or any sound-making object that's in the water, like sonar and things like that, you can imagine that it's important for sound to travel through liquids and for us to understand how sound waves can travel through liquids. So, there's a really cool video here I found, and all it is a sort of a visual representation of sound waves. It's simply pieces of foam that vibrate differently based on the kind of sound that you hear. So it's kind of like creating sound waves. What's really cool about it is you can see all the different solids transferring and visually representing energy as it moves through a system. You can also see very cool things like parts of a wave, like wavelength and amplitude and crest. It's pretty cool. Good proof of how sound and energy can travel through different mediums. So our goal today was to describe how sound energy is transferred by waves. And to wrap it all up today, I've got a great YouTube video. Takes a couple minutes, but it's well worth it to get to see a little bit about the science of sound and how we see, how we hear, and how sound is made. So we'll check that out, and we'll end with that. Thanks so much.
All right, I'm here at the Children's Museum of Virginia, located in Portsmouth, Virginia. And this is Leslie Bowie, the museum's curator. Hi, Leslie.
Hi, Van. I understand you want to learn about sounds.
Yeah, I want to learn about how sound works, and especially how sound travels.
Well, let's have a look at some of our exhibits and get the answers to those questions.
Okay.
The Children's Museum of Virginia is a place where kids can experience science firsthand. Here they can feel it, touch it, explore it, learn it. Let's first consider how sound is produced. When sounds travel, we actually are hearing how the vibrations affect the air molecules. A way I can demonstrate this is with the slinky. Van, hold the other end, please. What we perceive as sound is due to the alternate squeezing and stretching of molecules through the air. This we refer to as sound waves. Sound waves travel through the air at 344 meters per second. They travel slower than light. You can see this for yourself the next time you see a thunderstorm. You can work out how far away the storm is from you by timing the interval between the lightning and the clap of thunder. A storm is about 1 mile away for every 5 seconds you count, or 1 kilometer for every 3 seconds. Now that you know what sound is and how fast it travels, let's do some testing. What do you notice?
The longer the tube, the lower the pitch.
Well, sure. The air molecules in the long tube vibrate more slowly, producing a lower sound. Higher sounds vibrate more quickly. The difference in the number of vibrations per second we refer to as pitch. Want to try?
Okay. Cool.
We can also use a recorder to demonstrate pitch. You use your fingers to lengthen and shorten the tube and create higher and lower notes.
Well, that's great, but how do you make it louder?
Well, with a recorder, just simply by blowing more air into the tube. But there's another way to make sounds louder, and that's to focus sound. Let's come have a look.
Okay.
Here, the parabolic dish collects sound from a huge area and funnels it right to this point. If you're standing in just the right place, you can even hear a whisper.
So Van, why was Mr. Murphy only bothered by your sound?
Wait, somebody just asked me about Mr. Murphy. Who asked that question?
Well, Van, I'd like to introduce you to Dr. Lynette Roth. Dr. Roth is an audiologist. She specializes in hearing problems.
Oh, you mean like Mr. Murphy? Well, the question I have is, how come he singled out my band when there were so many other noises in the neighborhood?
It might be, Van, like many older people, you couldn't hear the higher frequency of noise that came from the other sound sources.
The higher pitches? Why?
Let me explain how the ear works first. Sound waves travel through the air and enter the ear canal, causing the eardrum to vibrate. The vibrations from the eardrum cause the 3 bones in the middle ear to move. The last bone is called the stirrup. The stirrup is attached to a thin membrane. On the other side of this membrane is fluid, housed inside a curled snail-shaped tube called the cochlea. The vibrations from the stirrup causes this membrane to flex, which in turn sets the fluid into motion. The moving fluid tickles thousands of delicate microscopic hair-like cells called cilia. The cilia convert the vibrations into electric nerve impulses, which the brain interprets as sound. High frequencies are heard by the cilia at the beginning of the cochlea. Lower frequencies are heard at the end. If sound intensity is too great, or if it happens for a prolonged period of time, the cells will die at the beginning of the cochlea. Sound energy or intensity is measured in decibels. Generally speaking, the human ear can comfortably hear between 10 to 80 decibels. A quiet library typically registers between 40 to 60 decibels, while a loud rock concert registers above 110 decibels. Van, it's likely Mr. Murphy has lost some of his ability to hear high frequencies.
So this explains why Mr. Murphy singled out our band.
Yes, Van, but I'm more concerned about the ear safety of young people, and in particular the noodles. Be careful how loud you practice your music, not for Mr. Murphy's comfort, but for your safety as well.
You bet. Dr. Roth, Mrs. Bowie, thanks for letting me come over to the Children's Museum of Virginia to learn about sound and how the ear works. Okay, I now have a better understanding of the science of sound and how people hear, but how do I control the amount of sound coming from my garage? Well, to find the answer to that, we're going to go back to Shelley at NASA Langley to see what she's learning about noise abatement. Perhaps she can pick up a tip or two I can use. Meanwhile, I'll share this information with my band, and I'll catch you later.